Next up, we have Jake and Reinhardt from SmithGroup, where I work. Very happy to have them here to talk about some of their tools and some of what they're doing with our pack team, which I'm sure they'll be able to tell you a little bit about. So happy to have you guys. How are you guys doing today?
Great. Thanks for having us, Dana.
Really happy you could make it. And I got it over here.
Sweet. Sounds good. We'll get started over here. So my name is Jake Chevrier. I've been with SmithGroup a little over a year now. I work in computation design and analytics for, as Dana said, our newly formed team. It's the PACT, or the Performance Analytics and Climate Impact Team.
Hi, everyone. My name is Reinhardt Swart. I'm a lighting and data lighting designer, as well as working with the PACT team. So today we want to talk about a couple items. Go to the next slide here. Perfect. Thank you. We do a lot of analysis for building performance, but today we want to focus on the integrated approach and what that means versus the traditional workflow, and really what ingredients you need, the timing, the teaming, and the tooling to make that happen. And then we're going to focus a little bit on translating architecture into data and leveraging this data to help inform design decisions as the decisions are being made. It's not a run and review process. It's more of a informed design space so that we could work at the speed of design. So the traditional design approach goes something like this. We wait for a building to be given to us by the architects, and they ask us to tell us how good they're doing. And we can run that analysis, and that's helpful, but it doesn't necessarily help us to create design decisions for better performing buildings. And so a better way of working would be to flip this process, would be to have the analysis run in advance preemptively, or potentially at the very least at the same time as when the architecture team is designing their building, so that we can inform decisions such as window to wall ratio, massing, the orientation, different programming, all these things from a daylighting and energy standpoint in our particular case, performance-wise, has an impact on the architectural design decisions. To do this effectively, a couple of things need to happen. First, timing. So of course we can be involved at any stage during the process, but most importantly is to be involved at the very beginning when we have the most impact for a little bit of the cost. I think the presentation before us just mentioned that same type of idea, and we want to reiterate that this is critical. The issue is that oftentimes the designs aren't quite baked yet, which is an opportunity, but also a challenge. And so how do we address this in design? We would argue through computation and parametrics, which we'll show you in a little bit here. Next slide, please. Yep. So when you think about the normal design way of working, lots of specialists, lots of smart people informing the design decisions. I would say this is more of an interdisciplinary way of working. I think a better way would be a multidisciplinary or even transdisciplinary approach, recognizing that all of these design decisions actually involve a bunch of specialists and that there's competing criteria often to get to a solution. And very often it's not just one optimal solution, but many other factors in addition to what we see on the screen here.
All right. And forewarned, this is where we kind of get in the weeds a little bit. So you guys are familiar with turning architecture into data. It's the same kind of concept here. We were really trying to take that architectural design problem, what we see on the left, the architecture, link it through a bunch of tools and transform that into data that can create this cyclical loop between analysis and the design problem. So mainly we work in Rhino and Grasshopper, but a lot of our workflows bring that back into the Revit environment for the documentation and detailing. How does this work as a process? It's a 4-step kind of process. We model the design decisions first. We're trying to get ahead of the design process. So we work with the design team, figure out what those parameters could be, come up with a model, and then we simulate all those iterations and create what's called a design space. Think of all the different parameters that we put in, and then we have a multi-dimensional model that we can pull from. We check out the performance metrics. So then we start diving into the data. We look for trends in that data. We look for the best performers. And then once we have those bucketed lists of options, we feed those back to the architect and actually integrate it into the process, into the project. So that first step looks something like this. It's a parametric model. We work closely with the design team to come up with all the different iterations of what they're thinking could be possible within this project. It's impossible to capture everything, but at least we can start abstracting and forming what we call a design space. So if we picture what that looks like, we might have fin depth, window to wall ratio, ceiling height, all these different parameters are creating this massive design space. And this is just 3 here, but you can have multi dimensions to all of these iterations. So then we take those, we simulate all those, and we pull out the data. As we're simulating, we're recording all the necessary data to make that informed design process. Once we have that data, we usually use the parallel coordinate plot, the spaghetti junction, as Reinhardt calls it, over here, where we have the inputs in black. So we're looking at that fin depth again, maybe that window width and that ceiling height. And then we can start looking at that with all our different metrics. And these can be open for whatever metrics that your specific project is interested in. Once we have all that, once we've selected our options, we create a cyclical process where we can take those options and transform them actually into Revit families, curtain wall families, as you see here. So now we'll talk about a use case where we did this. This is a lab building in California. The design team brought us in early to kind of look at window to wall ratio. What type of window? Do they want a ribbon window? Do they want a punch window? Or what we call a vertical window versus a ribbon option? But they're also really curious about a shading technique. They wanted to, it's basically an extruded building, glass facade. So we wanted to create some texture. So we were working with them to help them figure out the shading technique that's also going to bring a performance aspect to the project. Because we like method diagrams, we created a diagram for this, and it played out something like this, where we optimize that floor plate shape. We translate that into design surfaces, panelize those design surfaces into smaller modules. We run the energy and daylight once we have those panels. Then that energy and daylight analysis actually informs the shaping and the shading for those panels. Then we link that to Rhino to Revit, and those get pushed into our architectural facade model here. So I'll walk through those steps a little bit here. We had what we called the wrinkle. This project had, the facade was a wrinkle. So we were looking at optimizing that shape in plan so that we could get the minimum panel widths. This may make it easier down the road during construction, and we won't have all these one-off odd size panels. So we're trying to get ahead of that from the very start of the process. So they gave us the overall shape, and we started using this multi-ejection optimization tool to kind of figure out if there's an ideal setup for that configuration. Once we had that, we got down to 6 panel widths. I think the first one they gave me was at 11 panel widths. So we already reduced the panels right off the bat. Once we have that, we turn it into what I'm calling design surfaces. And then from those working points in the last slide shown here, we can actually panelize those and start looking at it from an architectural standpoint of, okay, is this an opaque panel? Is this a glazed panel? What's the shading technique applied there? And so on.
Yeah, thank you. So we've just talked about the top 3 sort of areas there, steps there. And the next thing I want to talk about or highlight is the energy and daylight analysis, the orange one there in the middle. And I think this is critically important because we are informing the design by pretty stringent daylighting and energy analysis to help back sort of the decisions that the team is making. And we're interested in pretty detailed items. So if you go to the, so all these would inform the subpanels, which we then document, and we'll get to in just a moment. But if you go to the next slide, what we're dealing with is quite a unique challenge because we're dealing with a bunch of parameters and an infinite many solutions, or close to, right? So, I mean, if you look at the glazing options, it's not just the window to wall ratio. In this particular case, it has to do with if it's a ribbon glass, what is the height of the sill versus the header? If it's punched windows, what is the spacing between the punched windows? So those relate to window to wall ratio, but they do make a difference as far as daylighting, for instance, glare or view. And so we had to model all those possible combinations. On top of that, we have our shading parameters. So for instance, you look at the shading, spacing the depth ratios of these louvers or these tiny baguettes, spacing depth ratios or dimensions there. So if you sort of layer those on top of each other, you can create what you see on the right there, which is a diagram trying to illustrate all the possible combinations. Each one of these lines starts to represent a possible combination of glazing and shading. And those are the metrics that we're tracking in this particular case. So you'll see here for each facade, we have multiple iterations. And the question for us is, how many of these particular options do we want per facade? Because the facades perform differently depending on the criteria. So what we did is we ran this through Rhino and Grasshopper using Climate Studio for daylighting and Energy Plus for energy. For daylighting, we wanted to maximize spatial daylight autonomy, while for energy, we wanted to reduce the peak cooling load. And so as you can surmise, these criteria oftentimes are competing, and there's not often one optimal solution. It's a compromise between the metrics with other metrics as well, right? Aesthetics, cost, those are design decisions that are real and need to be accounted for. And so this is generally how we simulated the analysis. On the next slide, you'll see a parametric workflow. So we're using Grasshopper, a visual scripting interface for Rhino, to build our geometry on the far left, first box. In the middle is our analysis engine. So there we're running it through Climate Studio and Energy Plus. And we're using Calibri on the far right to iterate through all those combinations and record the data. So the graphic that you see on the right here, behind the scenes, is full scale daylighting, annual daylighting analysis, as well as energy analysis for each of these different options. And what we're doing is we're plotting that, you see on the bottom right there, across different graphs or different metrics to start to understand the different trends based on facade, east, west, north, south, etc. So this is happening all behind the scenes. And the thing that we're interested in is the next step, which Jake sort of mentioned there in his diagram a little earlier, is that each one of these dots represents a possible solution. And so what we're doing is we're mapping all the solutions out for ourselves and for the architect to understand the major trends. So if we look at just the south here, for instance, we have 292 options in the parameters that we chose. And what we're looking at is mean UDI on the x-axis, useful daylight analysis, illuminance, and then peak cooling on the y-axis. Our goal is to maximize the mean UDI while minimizing the peak cooling. So we said if we have an SDA of at least 55%, that's a lead metric, and then a peak cooling reduction of at least 10% or 5%, that gives us a bucket that you see here. It's a more stringent bucket that says these are better performing options. Our goal here is not to dictate the design. It's to say out of all of the options and solutions that we just explored, these are the major trends, and these are the ones that are doing better. Consider using more of these and less of the others. Right? We don't want to tell the architect what to do, but we can certainly inform them in the decisions that we're looking at. So with all those dots, what Jake and I did is we visualized some of the sort of the big four buckets, if you will. You can see on the bottom, within those buckets, there are multiple solutions, but we can then go to the design team and have a conversation. For instance, these parameters on the far left, if you use those in some sort of combination, it's less than optimal solution. It's not doing very well, and we would not recommend that. We could do better. Start using some of this glazing options, start using some of these shading options, and now we can increase our daylight while limiting our glare. We could do even better if we go to the best, for instance, and we can increase daylight substantially while maintaining the peak cooling load. And so we're starting to break down the design problem by looking at the parameters and the inputs required to create these different buckets.
So once we have those buckets, like Reinhardt said, we go back to the design team and we say, here's your options. And we kind of come together and we look at what is best. And in this case, for this project, we actually took a mix of these because they wanted to create this randomized textured pattern on the facade, because otherwise it's a pretty simple glass box, besides the wrinkle. The wrinkle is fun. So we started playing with the opaque versus glazed patterning on these facade, and I'm doing this all in Grasshopper. So I'm basically translating each one of these options as an option to be applied to every single piece or every single chunk of facade that's on this project. And each facade has a different shading technique. So all that's done in Grasshopper. And then once we have that applied, we can actually bake those panels back into Rhino. And what this does is it allows the design team to jump back in. Maybe we have a couple people who are comfortable in Grasshopper, but most of the design team wants to work within Rhino or Revit. So the process we developed was to actually bake these panels. And if you click on these panels, you'll actually see that there's embedded properties into those panels. So what we have shown here in the better and best buckets, all those shading options, if it's an opaque versus a glazed panel, that all gets translated into custom user properties for each one of these Rhino panels. So it's our way of giving control back to the design team because we might be over here in the weeds in our grasshopper analysis models, and then they don't know what's going on, or they don't know how to interact with it or change a patterning. So we found this to be a pretty good workflow where we can translate that back into Rhino geometry. That way they can jump in, they can click on this, change the panel type to glaze versus opaque. It just gives them another point of intervention, I think is the word that we're using. So once we have that, once we have those Rhino surfaces, we can actually use Rhino inside to bring that over to Revit. So we can open up Rhino within Revit, and we can read in those surfaces. All those surfaces have properties, and those properties for each panel can actually drive a custom Revit curtain wall family with all the same matching parameters. So I built this custom curtain wall panel, and it's being placed for every single instance of panel that we have here. The location, the height, the width is placing a curtain wall with those matching characteristics and shading parameters that we developed within the process earlier. So this is our way of bringing it all the way back from, actually, next slide is better for this. So this is our process for bringing it from that first optimized intervention that we did of optimizing that floor plate, looking at the panelization of the facade based on the optimization that we did, running our energy and daylight analysis, feeding that back in and applying those parameters to the subpanels. So we're actually literally informing the design process. We create one more design intervention point within Rhino that the architect can work with before transferring over to Revit. But then once they're comfortable with that, they can bring that all the way back to Revit. We can also do a cyclical loop where in Revit, we can actually read those parameters back in and apply them to the panel. So it does go both ways. And that was important for a design team to be able to cross those borders of the software. So it seems pretty complicated. It's our way of working across platforms. We have Revit, and it's a very great at documentation and all that. And we love doing our analysis within the Grasshopper Rhino environment. So this is a workflow that we've found to help us bridge those gaps between the software.
That was fantastic. And I'll say amazing graphics as well to visualize everything. One question that I had was, what tool are you guys using for lighting analysis within Rhino? Is it built into Rhino, or is it an add-in into Rhino?
Yeah, for daylighting. So there's multiple. We've used Honeybee and Ladybug, which are sort of Grasshopper-based modules. In this particular case, we used Climate Studio, which is a plugin for Rhino and Grasshopper.
I had never seen that logo. So I was like, what is that? I was so ready to post the Ladybug link. And I was like, that is not the Ladybug link.
We've used Ladybug too. Yeah, and Pollination and Honeybee.
Yeah.
Okay, and Pollination and Honeybee. Okay, so I'll put all four of those in the
And I think Climate Studio does have a Revit plugin. I haven't run analysis via that, but they all the daylighting graphics are from Climate Studio.
Fantastic. The other question that we had that's on the mural was, how do you account for multiple design decisions? So, you gave the example of windows, right? How would that kind of play into another design decision that you might want to analyze in this way?
Jake, you want to take that one?
Sure. So if we're looking at windows, for instance, actually, let's go back to I think this slide. This one has multiple design decisions, right? It's what type of window. So you have to come up with a parametric model. You have to think about it. How do you cram all these design decisions into a parametric model? So the first one, we look at the windows, like what's the shape of the windows, and we had to think about how to do this. But basically, we came down to the conclusion that, okay, if we panelize these faces of the facade, then we can run different iterations and different options there. But then we're also applying the shading. So for each one of these glazing iterations, you get a shading parameter on top of that. So you start getting these multi-dimensioned studies. And sometimes we have to reel ourselves back in because we'll get, 1,200 different options. And one thing that we're looking at in the future is actually using machine learning to start doing random forest models to explore that data set and pull out specific models that we should start running versus running all 1,200 iterations. So I guess the answer to your question is you can tack on different dimensions to any parametric model that you're looking at. So just takes
Well,
more
and just kind of
computation.
playing around with the different iterations, kind of that's what the human aspect is, right?
Yes.
Like kind of that kind of playing of what's most important and the conversation with the client, the back and forth with that. So
Very much. This process shown on the screen right here was in close alliance with the design team. We were talking with them and we were saying, okay, what are you trying to go for with the shading? So there's still definitely the design aspect. We're not trying to replace that. So it's more of working with them and seeing what's possible.
the data driven decisions, right?
Mhm. Exactly.
Absolutely. Well, thank you guys so much. That takes us exactly to 2 o'clock. We want to appreciate your time.